Now let's see the applications of X-ray. Two subjects will be discussed. The first one is X-ray diffraction. X-ray diffraction is used of wave interference to investigate the crystalline structure of the material. And the next one is computed tomography diagnostic device. Here tomography comes from ancient Greek, tomos and graph. So tomos means slice or section, and graph means to describe. So tomography implies slice imaging. Okay? So in this computed tomography, we will use X-ray. For baggage inspection at airports and this CT, we do not need to know the wavelength of X-ray. Thus, in this case, we can use the continuous X-ray source. However, for X-ray diffraction, we need to know the exact value of wavelength of the X-ray. Thus, in this case, we have to use the characteristic X-ray by filtering the X-ray source. We already discussed that. Let's first see the X-ray diffraction. The inside structure of crystalline solids is studied via X-ray diffraction. It detects X-ray beam interference patterns projected onto material. The inter-area distance of the crystalline structure can be determined using these detected interference patterns. We can develop a three-dimensional structure of the material by doing X-ray diffraction studies in several different crystallographic directions of the material. So we can see the three-dimensional structure of the metals using this X-ray diffraction. In the figure, X-ray beam is directed onto the surface of the material with an inter-area spacing of d. This crystal, this material, the inter-layer spacing is d. So X-ray beam is incident onto the surface of this material. Then the angle of incidence is the angle of X-ray is theta. Yeah. The X-ray beam is refracted from the material's surface. Surface is the surface of the material. So X-ray beam is refracted on the surface of the material. So in this refraction, the law of refraction is satisfied. Incident angle is the same is that of the refraction angle. That is the law of refraction. However, some X-ray beams, pass through the surface of the material and refracted by crystalline structure's second layer. So some of X-ray passes through the surface of material, passes through to the surface and refracted here from the second layer of the crystalline structure. Okay, so this X-ray, and then here two beams are mixed, right? So interference patterns, so two X-ray beams are combined, and then you can have the interference patterns. So these interference patterns are detected when two X-ray beams meet here. The difference in path between the two X-ray beams is 2D sine theta. So this black X-ray refracted here on the second layer, and this blue X-ray is refracted from the surface of the material. So there is a path difference between two X-rays. So this much, so green color. So this distance is d sine theta, and we have two path difference, so we have the path difference 2d sine theta. So the path difference between the beam refracted from the surface and X-ray beam refracted from the second layer is 2d sine theta. Okay. So constructive interference occurs if the path difference is a multiple of the X-ray wavelength, resulting in a strong X-ray signal. Therefore, the following is the condition for constructive interference. 2d sine theta is the multiple of the X-ray wavelength. Okay. If the incident angle will satisfy this condition, we can have a strong X-ray signal at that angle. So if we change the incident angle, then we can have several different the peak, X-ray peak, which represents the constructive interference of two X-rays. So that means 1, 2, 3, 4. So different strong X-ray signals. Using those signals, we can determine the interlayer distance d. Okay. We can obtain the interference signal as function of incident angle by changing the incident angle of the X-ray beam as illustrated in the figure. We can obtain this kind of X-ray diffraction patterns. Here we use the X-ray. Here a detector here. Sample is in between. So we can change the angle of incidence by rotating this X-ray source. Then we can have several peaks, okay, which represents the constructive interference. So this figure shows diffraction patterns produced by a nickel film blown on a glass substrate. So nickel film on glass substrate. Some constructive interference peaks. These peaks. So using some constructive interference peaks can be seen in this figure. We can calculate the interlayer distance d using the incident angle of these peaks and using this relationship. Okay. So we can determine the interlayer distance of this nickel film on the glass substrate. So in this way, we can obtain the interlayer distance d, and we do the same procedure for different direction, and then we can construct the three-dimensional structures of X-ray of the material. This X-ray diffraction technique is used to test the DNA structure. The first DNA structure, X-ray diffraction of DNA was obtained by Rosalind Franklin in 1952. So double helix model of DNA structure was first published in the Journal of Nature by James Watson and Francis Crick in 1953, based on the crucial X-ray diffraction image of DNA enabled as photo 51 from Rosalind Franklin in 1952. So Rosalind Franklin first obtained the X-ray diffraction pattern of DNA. Using this DNA patterns of the DNA, James Watson and Francis Crick described the double helix model of DNA structure. The X-ray diffraction image produced by Maurice Wilkins, Rosalind Franklin, and Raymond Gosling led to the deduction by James Watson and Francis Crick of the three-dimensional helical nature of DNA. The first XRD patterns of DNA was obtained by Rosalind Franklin, and after that Maurice Wilkins and Raymond Gosling obtained the same kinds of X-ray diffraction of the DNA, and using these X-ray diffraction patterns, James Watson and Francis Crick succeeded in explaining the double helix model of DNA structure. In 1962, these are three portions: Maurice Wilkins, James Watson, and Francis Crick won the Nobel Prize for medicine. At this moment, Rosalind Franklin was already dead because of cancer, so she didn't receive the Nobel Prize. Now let's see the computed tomography. So we call the CT. The intensity of the X-ray beam I0 is reduced after passing through a certain material of thickness X. If an X-ray beam of intensity I0, S0, penetrates a material of thickness X, the X-ray beam's intensity is reduced as follows. So I equal I0 exponential minus mu x. Here, mu represents the material's absorption coefficients. X is the thickness of the material. This equation can be rewritten as follows. Mu equal absorption coefficient is written as this equation. So the intensity ratio of the transmitted X-ray beam to the incident X-ray beam determines the absorption coefficient according to this equation. So absorption coefficient can be determined by the intensity ratio of transmitted X-ray beam to the incident X-ray beam. Okay. We can construct an image of the human body using the absorption coefficient as an image contrast parameter if we can determine the absorption coefficient of X-ray at the specific positions of the human body. So X-ray actually sweep the human body, then we can have some image slice. Okay. In the image slice, there are so many different tissues and bones. If we can determine the position dependent or dependent X-ray absorption coefficient, then we can construct the grayscale image using these absorption coefficients. Right? So this is the basic concept of X-ray CT. The equation I equal I0 exponential minus ux represents the relation between incident and transmitted X-ray intensities. The transmitted X-ray intensity decreases as thickness X increases, obviously. Additionally, for high absorption coefficient material, the transmitted X-ray intensity is significantly reduced. Okay. Exponential expression. So, if the absorption coefficient of material is very high, then X-ray intensity, transmitted X-ray intensity is greatly reduced. The first commercially viable CT scanner was invented by Godfrey Hausen field in the United Kingdom. This portion. Alan Cormack of Tufts University independently invented a similar process. So Alan Cormack, this portion. He is actually a particle physics physicist, and Hausenfield is electrical engineer. So Hausenfield and Cormack shared 1979 Nobel Prize in Medicine. So the first CT scanner appears in the year of 1979. So in 1980s, these X-ray CT scanners are widely used in hospital to diagnose the disease. Let's take a look at the X-ray beams sweeping across a slice of the body as depicted in figure. So there's a slice of the body. So X-ray beam sweeps, then we can have image slice. So this represents image slice. After being observed by various tissues on its path through the body, the initial intensity I0 of the X-ray beam, represented as a borderline, these lines, is detected as I, which is less than I0. And the intensities can be represented by these equations. Okay. So the following is the formula for X-ray absorption via the body. So that's transmitted X-ray and initial intensity of X-ray beam, and mu I and delta xi represents the tissues which is encountered by the X-ray beam passing through the body, and delta xi is the thickness of the tissue. As there are various kinds of tissue and bones, so we can express the transmitted X-ray beam intensity by this equation. So mu11, mu12 at testa represents the absorption coefficients of the various tissues, and we can divide this image slice by n by m pixels. Okay, this rectangular region represents a pixel. So image slice can be represented by m by m pixels. The absorption coefficient and thickness of the particular tissue are denoted by mu I and delta xi respectively in this expression. And the above equation is rewritten as this relationship. So Pi represents the logarithm of the intensity ratio of instant beam to the transmitted beam to the instant beam. We set all the delta xi to the same value, delta x, since the slice was divided into the same pixels as illustrated in the figure. So we divided the image slice with the same size the pixels. So same size the pixels. So this image plane is made up of n by m pixels. Consider a slice shown in the figure, which is made up of m by n pixels. So this image plane is composed of m by n pixels. If the X-ray is swept across the slice once, so X-ray is instant in this direction, and the detectors are here. Okay. So we have n detectors here. Okay. So if the X-ray is swept across slice once, then we have the n data. Okay. So we have n detectors here. So once the X-ray is swept across the image plane, we can obtain the n data of the Pi or II. However, in order to construct an image of the slice, we will require data m by n of Pi's. Okay. So we need the absorption coefficients of each pixels. So m by n pixels, but we have only n data for one crossing of X-rays through the image plane. So we need more data. Okay. So to get more data, we will rotate X-ray source. So we rotate the X-ray source and sweep the slice again to get more data. To get m by n data, we must rotate the X-ray m times. For one sweep, we can have n data, but we need m by n data. So to get m by n data, we must rotate the X-ray m times. Okay. So each time, altering the angle by 180 divided by m. So we rotate the X-ray source m times and obtain the data. Then we can have sufficient data to determine the absorption coefficient of the m by n pixels. So The absorption coefficients of all pixels n by n pixels can then be obtained by solving the n by n linear equations. So once we determine the all absorption coefficient of the pixels, then we can construct image using grayscale. Right. So the grayscale image of the slice is then constructed using these absorption coefficients. So using these processes, we can obtain the CT image. Let's see a very simple example. Consider slice which is made up of 2 by 2 pixels as shown in this figure. The four measurements are performed by rotating the X-ray as shown in the figure. The first, we sweep the X-ray beam from bottom to up, so 0 angle, 0 degree. Then we can have the intensity, X-ray intensities of 7 and 8 are obtained. Okay. When the slice is swept from bottom to top. Okay. So we have two data, 7 and 8. When the X-ray is swept from left to right, so 90 degrees, the X-ray intensities of 4 and 11 are obtained. Okay. And the X-ray intensities of 6 and 9, 6 in this direction, that's 135 degrees, and 9 here, 225 degrees, are then obtained. So by four measurements, 0 angle, 90 degree angle, 135, 225 angles, so we have four measurements. So we can have this kind of data. The absorption coefficients of the 4 pixels can be obtained by using these data. Okay. Let's see the equation here. So 0 degree angle in this direction, mu1 plus mu3 equals 7, and mu2 plus mu4 is 8, and in 90 degree angle here, mu1 plus mu2 equal 4, and mu3 plus mu4 is 11, and in this direction, so 135 angle, mu1 plus mu4 equals 6. And in this direction, mu2 plus mu3 equal 9. So we have linear equation. So it is simple to calculate. First, let's see the these two equations, mu1, mu3, and this. Subtract these two equations, then we can have this relation. And if we subtract this equation from this equation, we can have this relationship. So now using this equation and this equation, we can determine the mu2 and mu3. And using this equation, this relation, and this relation here, this here, we can determine mu4. And if we use this mu4 here, then we finally determine the mu1. Okay. So in this way, using this data, we can determine the absorption coefficients of the four pixels. So here 1, 3, 6, 5. So using a grayscale, we can obtain this image. Absorption coefficient is very large here, so we can put darker color here, and this one, so bright color here, and in between as well, so we can obtain the CT image. We can also determine the absorption coefficient of the pixels using iterative reconstruction method. Let's see this. Okay, first 0 degree direction, this direction. So X-ray is passing through 1 and 2. Then we have data 4. So 0 direction. Oh no, not this one. 0 direction is this direction, right? This is 90 direction. So first see the 0 direction and this direction here. So 0 direction, direction. We have 7 here. Okay. So we have 2 columns or 2 pixels. So half of data 7 is put both in 1 and 3. So this makes 7, right? And here we have 8. So also half of the data 8 is put both in 2 and 4. So 4 and 4 here. Now let's see the 90 degree direction. So in this direction, we have data 4. So the data of the first row is 4, so that's 4. But here we put the 3.5 and 4 here. So sum of these two values gives 7.5, right? The sum of these two values in gives 7.5. But actually our data is 4. So the difference is 3.5. So to satisfy the data 4, we have to subtract the value, the difference of the 7.5 minus 4, 3.5, right? Half of that, the 1.7. So we have to add subtract. Yes, we have to subtract 1.5 from here and here. So 3.5 minus 1.75 gives 1.75. So we put the 1.75 here. And 4 minus 1.75 is 2.25 here. So we put 2.5 here, put here. And now the second one here gives 11. But here we can have sum of 7.5, but data is 11. The data of second row is 11, but the sum of two values in 3 and 4 is 7.5. So to satisfy the data 11, we have to add, okay, the value of 1.75. So if we add 1.75 here, that gives 5.25, and 4 or add 1.75 gives 5.75 here. So finally, let's see the this direction. This direction. So this direction, right? 135 degree direction. Data is 6, right? But if we add up these two values, gives 7.5, right? So the sum of 1 and 4 is 7.5. This is 7.5. So that's different, right? Difference is 1.5 divided by 2 gives 0.75. So you have to subtract the 0.75 here gives 1, and this pixel gives 5. And finally, 225 degree direction, this direction, the data gives 9, but we have here 7.5. So difference is 1.5, and half of that is 0.75. So we have to add 0.75 in this direction. So it gives 3 and 6. So we can have the same results shown in the previous slide. So using these values, we can construct the image by using grayscale. Now let's see the PET-CT and SPECT-CT images. PET image, in PET image, we are using the radionuclide, actually beta plus decay nuclide is used, and then this beta plus radionuclide is observed by most of them are observed by cancer, and there the gamma ray is emitted, and those gamma rays are detected, and we can have these PET images. So for PET images, you can see here it's very hard to specify the position of the organ. So if we combine this image with the image of CT image, then we can specify the position of the disease very clearly. So at this position, cancer tissues are here, And in the PET image, cancer tissues are observed most of the radionuclide, and most of radionuclides are emitted from these cancer tissues. But it's very hard to specify the position of the organ in this PET image, but CT image gives the very clear image of the organ, so we can combine these two images. We can specify the cancer position of cancer tissue very clearly. So we have the PET-CT combined device to diagnose the disease more clearly. So this PET-CT device are widely used for detecting the cancer tissues. The same similar, the device PET-CT, SPECT-CT. PET is positron emission tomography, so we use the beta plus radionuclide. In the SPECT, single photon emission computed tomography, in this device we use the beta minus radionuclide, and a little different, but the basic idea is the same. Radionuclide are injected into human body, and those radionuclides, most of them are observed by the cancer tissues, and gamma rays are emitted from the cancer tissues, and those gamma rays are detected outside, and then we can obtain this kind of radioactivity image, but the position of the cancer tissues, so organs, are not clear. So if we use the CT image combined, then we can clearly pinpoint the position of the cancer tissues organs. So for these purposes, PET-CT and SPECT-CT are widely used nowadays for cancer diagnosis.